Hi, I'm Bob. Welcome back to 5-Minute Econometrics. In the previous video, we discussed the Bruch-Pagan test for heteroskedasticity. The test involves running an auxiliary regression of the squared OLS residuals on all the explanatory variables in the model. The purpose of doing this is to determine whether the error term in the original model has an non-constant variance. Today, we will explore the white test for heteroskedasticity. The difference between the white test and the BP test is that the auxiliary model in the white test includes not only all the explanatory variables, but also their squares and cross products. The BP test can be seen as a special case of the white test. Since the auxiliary regression in the white test includes more coefficients, it is a more stringent test than the BP test. For the same model, we are more likely to reject the null hypothesis of homoskedasticity and find stronger evidence against homoskedasticity in the white test than in the BP test. For a multiple linear regression model, the null hypothesis in the white test is the homoskedasticity assumption. If we find evidence against it, we conclude that the model suffers from heteroskedasticity. The auxiliary model in the white test regresses the squared residuals on all explanatory variables, their squares, and cross products. The null hypothesis is equivalent to all the coefficients of the explanatory variables, squares, and cross products being 0. When there are k explanatory variables, the number of coefficients could be large. For example, if the original model has 3 explanatory variables, the auxiliary model in the white test looks like this. There were 9 coefficients or 9 restrictions in the white test. For a model with 6 explanatory variables, the auxiliary regression involves 27 slope coefficients. To overcome this inconvenience, an equivalent version of the white test uses only 2 regressors in the auxiliary model, no matter how many explanatory variables in the original model. Recall that the OLS fitted value is a linear function of all the explanatory variables. If we square the fitted values, we obtain all the squares and cross products of the explanatory variables. Now, the auxiliary model becomes the regression of the squared OLS residuals on the OLS fitted values and their squared term. The null hypothesis of the white test has only 2 restrictions. If we reject it, we suspect the model exhibits heteroskedasticity. We can show that the 2 versions of the white test are equivalent. Here's the case with 2 explanatory variables in the original model. The auxiliary regression for the first version of the white test has 5 slope coefficients, whereas that for the second version has 2 slope coefficients. After plugging in the expression of the fit value, we can show the equivalence of the two versions. There were two steps to do the White test for heteroskedasticity. For a multiple linear model with k explanatory variables, we estimate the model by OLS in the first step. We obtain the residuals and the fit values after regression. We then compute their squares. By doing so, we have all the elements for the auxiliary regression. In the second step, we run the auxiliary regression of the squared OLS residuals on the fit values and their squares. Notice that there were always two regressors in the auxiliary model, regardless of the number of explanatory variables in the original model. The null hypothesis is that the two slope coefficients are zero. We can compute the LM statistic or the F statistic for the Y test. We continue using the same hourly wage example from the previous topics. The model connects workers' hourly wages to their years of education, age, number of children, gender, and other demographic characteristics. We use the logarithm of the hourly wage as the outcome variable. After running the OLS regression, we use the predict command with the residuals option to store the OLS residuals for each observation in a new variable called mu_hat. The predict command with the XB option saves the fit values. I name it LWage_hat. We then square the residuals and the fit values. Next, we run the auxiliary regression. We regress the squared residuals on the fit values and the squared fit values. The LM statistic for the null hypothesis equals the sample size times the R squared, which is 6.72. The p-value is 0.035. We reject the null hypothesis of homoskedasticity at any significance level above 3.5%. Compared to the BP test, the White test provides stronger evidence of heteroskedasticity. Recall that we fail to reject homoskedasticity hypothesis at 5, 10, or 15% in the BP test. By contrast, we can only fail to reject the homoskedasticity hypothesis at significant levels below 3.5% in the White test. The F statistic for the overall significance gives similar results. In addition to computing it by hand, Stata directly displays the overall F statistic and its p-value in the results window. For the model using the level form of hourly wage as the outcome variable, the Y test reaches the same conclusion as the BP test. The LM statistic is large and its p-value is close to 0. It is strong evidence of heteroskedasticity. Today, we explored the White test for heteroskedasticity. In the auxiliary model, we regress the squared residual on the fit value and its square term. Then we compute the LM or the F statistic for the overall significance of the auxiliary model. If the statistic is large and the p-value is close to 0, we reject the null hypothesis of homoskedasticity and conclude that the original model exhibits heteroskedasticity. Thank you so much for watching this video. See you soon. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.